Yeah, fasteners are the way to go. So last week, we kind of looked at applications of digital to analog converters and how you can have some control over physical systems with your microcontroller. There are a ton more, and we've mentioned a few that are in our car as well, specifically for that torque path from the foot pedal through to the VCU and then out to the Curtis inverter, where we emulate a 0 to 5 volt analog signal with a DAC that's on the VCU. So far, we've also talked about in these sessions GPIOs, right? You have inputs, outputs, pull-ups and pull-downs. And then on your outputs, you can be push-pull, which means you are outputting a high to your logic level and a low to ground. Or you can just be, so this is push-pull, or you can just be open drain, where you're only sending a low to ground, and then for your high, you just leave it floating. And usually you want to accompany this with a pull-up resistor. Right? And that allows us a number of different things. That means the user can sort of choose the logic level they want up here with whatever pull-up resistor they put. It also means that we can have multiple systems sharing the same line and sort of have an ORing logic towards them so that they don't accidentally send any shorts. But in general, you'll see an application of this today when we talk about serial communication protocols. We've also mentioned some of the analog side, so analog to digital converter, as well as digital to analog converter. And for both of these, what was really important was the resolution. So however many bits you have to play with. Your analog voltage reference. So that's basically the full scale range that you can get for either sampling your analog signal or sending out your analog signal. And then the sampling rate is important as well, especially for ADC. We also briefly mentioned pulse width modulation. So that's a form of GPIO, right? It's only digital, logic high or logic low, pulse width modulation. And with that, we were able to vary the width of the pulse based on a set frequency and also a set duty cycle as well. Frequency and duty cycle was just the ratio of how long our pulse was high to the ratio of the overall period, right? And period is just 1 over frequency. Cycle, nice. Any questions from what we've chatted about in the past few weeks so far? Cool. Silence is yes or no. Basically, we don't know. So one thing we haven't talked about, and we sort of alluded to a bunch of times, is how do you actually interface with these systems, especially if they're outside of your microcontroller, right? If I have my microcontroller here, right, it's a little chip, and my digital to analog converter is off the chip. Maybe I don't have that peripheral inside my microcontroller, or I wanted to pick one with a specific set of parameters. I need to talk to it in some way, right? Same way if I had an external ADC, right? I want to collect data from it as it samples the analog side and spits out digital. How do I actually get that digital? And what does that look like? Well, smarter people than us sort of figured this out, so we don't really have to redo it from scratch. But what used to happen, and still happens sometimes, but in old computers, what they used were more parallel communication protocols, not serial. And I'll talk a little bit about the differences between those things, right? Forgive me if I spelled parallel wrong. That's a tricky one. Parallel communication. So, right, parallel comms. And basically, the idea is that, so for your ADC, so let's say it was 10 bits. You had a 10-bit ADC. What that meant is that it converted the analog into a set of different levels, right? And you had 2 to the 10 different levels it could be. So usually we'd represent this by a 10-bit number, right? So you have, let's do an easier one actually. Let's just do 8 bits right now. Let's do 8 bits, right? So the total different number of levels we'd have is 2 to the 8 different levels for our digital signal. And usually you can represent this in a variable that's 8 bits wide, right? So an 8-bit variable could store our digital value. Now, how do we actually send those 8 bits from the ADC to the microcontroller, right? ADC to microcontroller. Well, what they used to do literally was send each bit on its own line. So you'd have an ADC like this. There's some pins that sample the analog side. And then to send 8 bits across, you'd have a wire for bit 0, a wire for bit 1, bit 2, bit 3, bit 4, bit 5, bit 6, bit 7, right? 0 all the way to 7. So it's 8 different bits. And on these wires would be the values, right? Like if I converted my analog signal to digital, maybe it'd be something like a 1, 1, 1, 0, 0, 1, 1, 0 would be the digital value. And so each of these bits would correspond to one of these lines. So I would send like a 0 on this line, a 1 on this line, 1, 0, 0, 1, 1, 1. Is that right? 0, 1, 1, 0, 0, 1, 1, 1. Yeah. And then this would go to your microcontroller, right? And you can imagine that people sort of got tired of sending so many wires across. So the downside to this is you're going to need to have at least 8 pins available on your microcontroller to actually read all of the 8 bits. And if your ADC is not on the same circuit board, for example, let's say it's somewhere else in our car, you would need 8 actual wires going across instead of maybe 8 little traces on a circuit board. So it gets really cumbersome, really expensive, a lot of work. And then you're going to have a lot of requirements on actually having 8 pins available here. And those pins are pretty valuable on the microcontroller where you're trying to do so many other things in a car, for example. So what people did was they invented something called the serial communication protocol. And the idea is that instead of sending each bit on its own line, we send all the bits one at a time. And let's keep it basic for now, but on a single line, for example. So instead of sending one line for the first bit, one line for the second bit, one line for the third bit, what we do instead is we send all of these on one line, one at a time. So we'd send a 0, and then it'd go across. Then we'd send a 1, and then it'd go across. And then another 1, go across. And then a 0, and it'd go across. And basically, you can imagine it as just a little pipe, right? It's a little, or maybe a little tunnel. Then you're constantly shoving one bit at a time through that tunnel until it gets to the microcontroller. And the microcontroller needs to wait there and accept each item as it comes out of the tunnel, right? One at a time. And so that's a serialized communication. Instead of all the bits being sent at one time in parallel, like in just one shot, you send 8 bits at a time. Now you're sending 1 at a time, 8 times. You can imagine, right? And now the benefit of this is that we no longer need 8 wires, right? We no longer need 8 pins on the microcontroller. We no longer need an ADC that has 8 pins here. All we need is 1 pin. 1 pin on a microcontroller could read all of the bits from the ADC. And so people really like this because it kept costs low. It kept like actual hardware sizes much smaller. We didn't need to have 8 pins, for example, available on the MCU, just 1 in this basic example. But you can imagine what's the trade-off, right? You don't get anything for free. And so it's pretty clear that it's a lot slower, right? If I'm sending 1 bit at a time through this tunnel, through this little tunnel here, okay, it's going to stay orange, then I'm going to lose the speed that I had before where just in one shot I could send 8 bits at a time and move on with my life, right? So they had to kind of increase the speeds a little bit, but in general, this parallel communication protocol will always be faster. And what people are doing now is, especially with these high-speed communication protocols inside computers and advanced processors, they basically do the serial communication. So this is parallel, right up here, parallel comms. And here's serial. You basically just do this repeated in a parallel bus. So you just have this sort of each line would be a little tunnel where you're sending data through. And that gets much faster. But serial communication protocols have become super popular because of basically how easy they are. Once you have the software side figured out, how to actually process each of these little bits as they come through, then it's super easy to just plug in one wire and get all your data. Now you can imagine that if I have my ADC or my DAC, so let's call him Alan. He's collecting data and he's super excited about it, right? He wants to send it to Elaine here, right? She's a microcontroller. Elaine's going to have no idea what Alan's talking about if he just starts spitting out random numbers at her, right? Serialized. It's like a 0 and then a 1 and then a 1. She's going to be like, well, does that correspond to the ADC voltage? Does it correspond to some other signal you're trying to tell me? They're basically speaking different languages. So what they usually have to do is agree on a language to start, right? So Elaine and Alan will agree, hey, we're going to talk in X language or Y language. And it's not necessarily the same language like a programming language, like the C or C++. It's a communication protocol, they're called. And so there are a bunch of different types, especially in the serial world. And basically picking different types, you'll do based on whatever priorities you have. Some are faster, some have less pins, some have more pins, some are slow, some allow you to talk to multiple people, right? Maybe we have a friend here who also wants to talk to these guys, so he wants to play as well. Some communication protocols allow that, some don't, right? And so you have different use cases for different versions. So we're going to start today with is something called UART. Any questions so far?
When you said bus, are you talking about a vehicle?
No. Which parts did I say bus at? I don't
You
know.
were talking about serial being a bus or some kind.
Yeah, thanks for mentioning that. That's common terminology, and thanks for calling me out on that. That people use often, usually for like a communication channel or like a tunnel. So usually they'll call like this tunnel that information is flowing through as a bus, especially if multiple people can contribute to this communication and talk amongst each other. Then a bus is very common in the terminology. And more so with parallel communication, to be honest, like the parallel bus. But it's very common to refer to any communication protocol as like the UART bus or the I2C bus or SPI bus, for example. So UART is the first one, pretty fundamental. So it stands for universal. Asynchronous. That's important. Receiver transmitter. So this is one of those languages that the sender and the receiver have agreed upon beforehand. And T is transmitter. You're not going to be able to communicate with anything if you have not agreed on a language beforehand. And that language is going to be pretty obvious because it's going to be determined by things like number of pins and wires used, what voltage levels you need, things like that. So universal asynchronous receiver oh man, I wrote transfer. That's wrong. Transmitter. So this is a very fundamental one. Sometimes it's known literally just as serial. Even though technically there are so many different serial communication protocols, this is one of the most fundamental, so people just call it serial. And so that's basically what you're opening up when you open up a serial terminal on your computer. So like something on maybe your Arduino serial viewer, or something like PuTTY or Hyperterm. If you open it up, I can open up one here now. So if I open up PuTTY, this is just a software you can download online. And it'll open, for example, a serial terminal. So there are a whole bunch of different ones, but we're looking at serial today. So you're going to pick, for example, whatever COM you have, and on Mac it looks a little different, but basically like easily just like which USB port you have. Although you can have multiple COMs, even if you only have a few USB ports. The speed, this is also known as the baud rate, number of data bits, stop bits, and then a few other safety checks here on the bottom. So serial is pretty useful, and it's what we use to communicate with our microcontrollers to the PC a lot, and even between microcontrollers. But like the most common application of this is from your computer here. To whatever MCU you have, right? And you can talk back and forth. It's not just one way, which is nice. MCU. Cool. And once we get into the details, there's actually a little converter you need here to go from UART to USB specifically, but we can talk about that somewhere else. Cool. So what does UART actually look like? So it's two lines. I have one item. So let's say it's my PC, my computer. I have my MCU. I have a transmit line and a receive line. Right? And usually people don't often say it's 3 lines, but theoretically you also need to connect grounds between these. It's always very important. If you're not connecting the ground, then you're not going to have the same voltage references. So let's look at it from the point of view of the microcontroller. So let's say this is the microcontroller's TX line, and this is the microcontroller's RX line. What's important to note, and that actually gets a little bit confusing, is that the microcontroller's transmit, so TX, needs to go to, if this is your ADC or your slave or your PC or your DAC, whatever you're talking to, the TX of the microcontroller has to go to the RX of whatever you're talking to, right? What the MCU is transmitting, the computer needs to be receiving, right? And it's the exact same the other way. Whatever the PC is sending out, transmitting, the microcontroller needs to be receiving, right? So whenever you're connecting two things over UART, you need to make sure they cross, right? Transmit goes to receive, and receive goes to transmit. And sometimes that's a little bit confusing because that's not the same for all protocols, but for UART it definitely is. Now, another really important thing about UART is that we mentioned it's asynchronous, right? We set that up here. And this is really one of the defining characteristics of UART versus other communications. All synchronous means is that it's the same sort of idea as if you and I started at one location together, we both had stopwatches, we synchronized them together, and then we go on our separate ways. And Monod will always have the same clock, will always have the same ground truth time to refer back to, because we're synchronizing them together. In UART, we're not. It's not a synchronous protocol. It is asynchronous. There's no actual dash here, but I'm just putting it there to be very clear. We're not sharing a ground truth clock to make sure we're sending things at the same time, at the same rate. The whole point of UART is that you basically agree on a particular speed beforehand. So do not share a common clock, right? And we agree on a speed beforehand, and we call that the baud rate, right? Sometimes people refer to that as the speed. If I'm sending you zeros and ones at 2 times the speed you expect to receive them, you're only going to get every second one, right? And so the microcontroller needs to agree on a certain baud rate. So one very common one is 9600. And for a very simple example, you can imagine this as the baud rate as bits per second, right? Once you get a little fancier, baud rate doesn't always equal bits per second. You can do some other very interesting things, but at its most basic, you can imagine baud rate as bits per second. So that means if I had those 8 bits to send, right, across, I could send 9600 of these every second. And so those are going out 9600 times a second. And this is configurable, this 9600 up here. Now, whatever you're talking to needs to agree, needs to say initially when it's first set up, hey, we agreed, we're using UART and we're using it at 9600 bits per second or 9600 baud rate. If we accidentally pick something else, let's say I picked a higher baud rate, maybe a lower baud rate. Honestly, I'm not sure if this is a real baud rate. 4800. I'm not going to get all the data. And usually you can actually see when they don't line up, because if I'm viewing data on my PC, like in a little terminal window, like I showed you opening up, usually you'll see that show up as a bunch of garbage, right? It actually looks like random wingdings characters and slashes and number signs, like someone's swearing at you, instead of the actual data you expect. So it's usually a good hint to see that, like, hey, actually, probably my baud rates don't line up if I'm just getting a bunch of garbage. But if my baud rates are similar, or are exact same, sorry, then I should get exactly the data that I expect. This is really important. That's the whole asynchronous nature of UART. It's that we're not going to share a system clock. We're not going to synchronize our stopwatches to make sure we're running at the same speed. We're going to agree on a predetermined baud rate beforehand to make sure that we can actually decode each other's information, right? And that goes the same way here. If the transmitter is sending the wrong baud rate, the microcontroller is not going to receive the right data. It's just going to receive a bunch of garbage. So that's really important. In other communication protocols, what you actually do is you send more wires, right? You actually send another one, and that would be your clock. If you're sending a clock wire in between microcontrollers, or in between your microcontroller and your slave, or your microcontroller and your PC, or ADC, or whatever you're talking to, then you're synchronizing the times together. Both systems know exactly what the ground truth clock is. And depending on how fast that clock is running, they know exactly at what rate to interpret the data at. But without this clock in UART, you need to be very, very clear that you've agreed on the same baud rate, right? They differ, it's not going to work. Does that make sense? Questions?
How is the baud rate set?
Cool. Thanks for asking. Yeah, so your skip message now. Yeah, exactly. You're right. Through code. That's it. So in our microcontroller, for example, we have this thing called Halcogen, and that's a little GUI where you can set different parameters for all of your peripherals. So inside Halcogen, it would look something like this. So like you have your window and your computer, and then we have a bunch of tabs up here. So you click on the little UART tab, UART, and then it'd say something like baud rate. And then a little drop down where you can pick whatever speed you want. So on the computer side, if you're talking to your computer, you see this here, speed. you can set that, right? So I could say I want 9600 or 1500, 115,200, or whatever speed you're looking for, so they are the same. And all Halcogen does for us, for the microcontroller side, is it just generates the code, right? It's just a shortcut. What actually happens is you just write those lines of code yourself, usually. But we have this little shortcut tool to do it for us, for the microcontroller side, right? MCU Halcogen. But it's definitely super configurable, and you can change it whenever you want. If you're talking to something like a chip you bought off of DigiKey online somewhere, so let's say I'm talking to an ADC, and it's giving me data out over UART, it's usually going to have a fixed baud rate or fixed speed. That's a big fixed baud rate. And you'll find that in the datasheet of the chip, right? This is something that the manufacturer's programmed into it, and it's going to spit data out at 9600 at a 9600 baud rate, and you're going to have to match that so you can actually get the right data from it. If you don't match that, then that's on you, right? You're just going to get data and you will have wasted your money. But it's your job to read the datasheet of this chip, find out what speed it communicates at, and then match that. And some of them have very fancy configurable ones, but a lot of the low-cost ones are just fixed. So we mentioned that UART has... Does that answer your question, Courtney?
Yeah, it does. Thank you.
Okay, great. So 2 lines, right? TX, RX, and those cross, right? TX on the microcontroller would have to go to RX of the ADC, and TX of the ADC would have to go to RX of the microcontroller, right? So people also call this a full duplex system. Full duplex. And all that means is that we can send and receive at the same time, right? While I'm sending stuff, I can be receiving stuff on the second pin, and it's not a problem. That makes it relatively quick. There are other communication protocols where you only have one line, right? I only have an MCU, ADC. Sometimes I don't have the benefit of 2 different lines. I just have one data line, right? And communication and data could flow one way or it could flow the other way. So you can imagine I can only do one at a time, right? I can be sending stuff, and the ADC gets it, then I have to stop sending, and then I can receive stuff on that same line. Now I need to listen, right? This is called half duplex, just fancy words. And you can imagine it's slower, right? And so everything's a trade-off, right? If I want more speed, I need more pins, right? I need more lines so I can transmit and receive at the same time. If I want less pins, I'm going to have to go slower, right? Because I have to share data back and forth. And that's essentially the same idea between parallel and serial, right? I can pay more for more pins and more wires and bigger chips and bigger sizes. And if I do that, I'll get more speed usually. Or if I'm constrained on my size and number of pins and cost, then I can sacrifice a little bit of speed and just share data lines and go bidirectionally. Cool. So what does a little data packet actually look like, right? So if I had a microcontroller, and let's look at the TX line. So we're sending data, right? And what it actually looks like is something like this. So let's say our logic level is 3v3, right? We know we can send a 0 or a 1 or a 0 or a 1. And that would be 0 volts and 3.3 volts, right? This 3v3 is just notation for 3.3 volts. So the way the system works, so if this is TX, starts here, we have a start bit, then we have, let me just draw this like this. This little dotted line is going to be the separation of each bit. Okay, and then we have data. So let's say we have our ADC, 1, 2, 3, 4, 5, 6, 7, 8. Just pretend these are equally spaced. Here, here. Cool. So what we did, each little rectangle represents one bit of data. Remember, we said we're sending them one at a time through our tunnel, right? One at a time. So the very first thing we send is a start bit. All this does is it tells whoever we're talking to that we've started. We've brought the line down to ground, down to 0 volts. And for one bit of data, we said, hey, we're going to start. And remember, this has to last as long as our baud rate defined, right? So if we are at 9,600 bits per second, that means each bit needs to take 1/9600th of a second, right? So I wish I knew how to do that math, but 1 over 9,600 is a little frightening. But that would be however long this would stay low for. So it'd stay low for 1/9600th of a second, then the next bit would start. And so the slave or the ADC or the PC, whoever's receiving this, needs to know, right? If it knows it's 9,600 bits per second, then it knows how long to expect one bit to last. And that's how it's going to decode it and split it up into different bits. So we start with the start bit. The next thing you need to agree upon is how many bits are you actually sending, right? If we noticed back in PuTTY, I should probably stop closing it. Serial. You can specify the number of data bits that are going across, right? If I wanted, I could say 16. Maybe I have a 16-bit ADC that's spitting out data. If I wanted, I could say 8. 8 is usually the standard. And what that means is that after the start bit, we're going to send you 8 bits of data. Right? So this is a 0, for example. This is a 1, 0, 1, 1, 0, 1, 0. Right? So 8, 1, 2, 3, 4, 5, 6, 7, 8. So those 8 bits of data go across one at a time to whoever we're talking to, right? And that's where the actual data and things that you're sending are held, right? This start bit is always there. This data is going to be changing based on whatever you want to send, right? And maybe that's little characters that you're typing, for example, like ASCII, like an A or a B or a C from a keyboard. It could be an 8-bit ADC reading. It could be anything you want. Right, so after the data section, so we have the start bit, we have 8 bits of data, and then usually we have a stop bit as well. And depending on the settings you pick, there might be something else here. So we'll leave this blank for now. But then usually we have a stop bit. And that's just a last bit to say, hey, we're done. You can parse the data now, and we're done. And sometimes people make this 2 bits or 1 bit. Again, I've closed PuTTY for the 18th time, but in there, I swear you can select it. So that's configurable up to you. Sometimes people put 2 here. Usually it depends on the application and whatever your partner that you're talking to is asking for. Now, before we... Yeah, please, John.
Why would you increase the start and stop bits? What's the point of that?
Yeah, that's a good question. Sometimes it's to give some time for the like the ADC or DAC or whatever you're talking to, maybe the PC, to just have time to respond and to process the data. Sometimes it's a safety thing to make sure that you're double checking to confirm that there's 2 stop bits as well on both sides. So if I'm sending 2 stop bits from the MCU side, I need to make sure I'm seeing 2 stop bits as well here. So basically, it's just could be another method of redundancy to make sure that everything's still working. But often it's one of those 2 cases. I usually just keep it at 1 since that's pretty standard.
Cool, thanks.
Yeah. Even better
How
for
does it-
safety is, yeah.
I was going to ask, how does it know the difference between just a regular bit and the stop bit?
Yeah, great question. That's defined on how you set up the number of bits in your data, right? After it has seen 8 bits come across, it should be expecting a stop bit at that point. In PuTTY, for example, in your code, if you had said 16 bits, right, it just counts, right? It counts for 16 until 16 are done. Then it waits for the stop bit, and then it can move on.
Oh, so it's like, I guess it's programmed to know how many bits to expect.
Exactly, yeah.
Okay.
That's
Okay,
right.
cool. Thanks.
Yeah, so in my PC, for example, I'd put in exactly how many I should be expecting. And whoever you're talking to needs to agree on that as well. Oh, I'm not going to close it this time. Okay.
If it's counting and it's expecting 8 bits, then why do we need the stop bit?
Yeah, usually it's a form of redundancy and a little bit of time for it to actually process the data. So sometimes you may get garbage at the end. Like it may just stay low or go high. Sorry. But it's just a form of indicating to the system that you started and stopped. And sometimes people even add like a restart condition. So basically, like, let's say I get a little greedy, right? And I'm the microcontroller. I'm over here. And I want to send 8 bits, but I want to send 8 bits 3 or 4 times really quickly, right? So let's say I have a whole sentence of letters. Each letter is 8 bits, but I want to send 10 of them. Sometimes what people do is restart the whole process. So they do a start bit, send their 8 bits of data, and then they leave it low for another start bit. And then they keep hold of this line and keep sending more and more data. And so if it doesn't do this transition of low to high here and stay high, then it may expect more data to show up. And that just saves time, so you don't have to stop and then wait and then restart another start bit, send your 8 bits of data, stop, then wait, then restart. You can just say start, send data, and then keep sending more and more and more data if the slave doesn't receive the stop bit.
I think it's worth mentioning that the start and stop bit are also for the synchronization, because even if the baud rate is 9600 as we set it, it's not going to be exactly that between the two things communicating. And so having the stop bit being pulled down again when you're sending the next message helps keep the messages synchronized.
Yeah, that's a great point. It's hard to keep a very consistent baud rate all the time. Like Mahmoud said, it's not going to be perfect. So yeah, that's a great point to bring up. It's really good for synchronization. And that's mostly because you don't share a clock, right? You're asynchronous, so you have to agree on a lot of things beforehand, and you have to make sure that everything is as synchronized as possible. So something else that usually shows up, and it's not in all, every single one, you can decide if you want it there or not, usually a parity bit. So that's like an error checking form to make sure that none of these bits were corrupted in the data sending. And usually at its most basic, you can have an even or odd parity. And all it does is it basically counts the number of ones you're sending. Right? So if I say that my parity is even for the system, right? And I can do that here, for example. I can say I want an even parity. So even, what that means is that the number of ones that I see should always be even, right? I don't know why I drew even to even, but parity bit. So the number of ones that show up always needs to be even, and obviously that can't always be, right? Maybe you'll have a number that has an odd number of ones, right? Let's say that, for example, this last one here was a 1 instead of a 0. Right, then we'd have 1, 2, 3, 4, 5 ones there. So what we do with the parity bit is to make it even, we just put a 1 there. That's done automatically by the UART handler. So it'll add a 1 there. Then the slave or whoever you're talking to checks to make sure that there's an even number of ones. And now there are, right? We had 5 ones here, which was odd, but we put a 1 here. So there's now 6 odds, which is even. Sorry, 6 ones, which is even. And the slave says, hey, we're in even parity, right? Okay, there's an even number of ones. That means everything should be good, right? Even number of ones. Everything's fine. This is an O. Now, you can imagine if something got corrupted, right? If accidentally a 0 was sent because some problem on the data line, maybe physically with the voltages, then the PC is going to say, okay, I got 1, 2, 3, 4, 5 ones. That's odd, but we're in even parity. So something must have gone wrong. So it knows that this data packet has been corrupted and is garbage, right? Now you can imagine this is not foolproof, right? What happens if 2 data bits go wrong? Right? If this also went to 0, then I'd have 1, 2, 3, 4 ones. Hey, it's even, everything's fine, right? So this is one of the most basic forms of error checking. It's not foolproof, but it can help for a very low cost like application, right? All you need to do is put an extra little bit here on the very end and agree on even or odd parity, and then you have a very basic form of error checking. You can do the same thing the other way, right? You can say, okay, even's cool. I want an odd parity instead, right? So I had a bunch of things here. So I had a 1, 0, 1, 0, 0, 1, 0, 1. So this is 4. Then in my parity bit, what I would do is put a 1 here, right? My system would send a 1 to make it an odd number of ones, right? 1, 2, 3, 4, 5. Then the PC here on the right can say, yep, I received an odd number and we are in odd parity, so everything's good. And if something went wrong, like let's say this accidentally sent a 0 due to some fault in the system, the PC would say, okay, I got a 1, 2, 3, 4 even number of ones. Okay, that's wrong because we're in odd parity. So I know there's a problem, right? And you can imagine as well, if I had 1, 0, 1, 0, 1, 1, 0, 1, 0, 0, 1, 1, 0, 1, that's 4. And we're in odd parity now, right? So we have 1, 2, 3, 4, 5 ones. Hey, it's already odd. In my parity bit, I can just put a 0, right? I don't have to be adding ones to make it odd because it already is odd. Then the PC will look at it and say, okay, we're in odd parity. How many ones are there? 1, 2, 3, 4, 5. Okay, that's an odd number of ones. Everything's good. So your parity bit will just make sure that you're sending either an even or odd number of ones based on whatever you decided beforehand. Any questions? So that's usually a pretty basic way of getting that error checking to see if something actually did go wrong in the communication protocol system. But again, like I said, 2 errors could cancel each other out. So it's not the most complicated.
Is there any disadvantage to this other than the messages being slower?
I don't think so. That's a good question. Like, I don't see how it would hurt you, um, except that you're spending an extra 96 hundredth of a second here, right, in your protocol, so it's a little slower. If you can think of a way where it's bad for you, that'd be cool to know.
It's because nobody ever uses it.
Yeah, it just like usually it's common to just leave it off because two things can cancel each other. And honestly, I haven't had a lot of problems, especially from just microcontroller to computer, with like bits getting modified accidentally or errors happening. So we just kind of chill, and don't use it. But I don't know. Maybe in a more harsh environment, people turned it on. Do you know if is it on in the BMS UART?
No, it's not.
And is that set like by the slave? It doesn't want it on, or can you configure that?
I'm not sure. It might have a register where you can control it because you can control the baud rate of the slaves.
Cool. Yeah, so we use UART in our car. From the master to the BMS slaves, and then they talk to more over there. But why we use it, it was defined by this chip, right? This chip wanted to talk in the UART communication protocol, so we have to oblige, right? We can't just say, hey, I don't like that, I want to talk in something else, and no real communication is going to happen. So you have to chat in that same language. There's also something called UART. Do you guys use that a lot at work, Mahmood? Or at all?
UART? What's that?
Yeah. Okay, I guess not. It's a synchronized UART, basically. Synchronous.
Nah.
Yeah. I don't understand why you'd use this over SPI, but UART it's kind of dumb how they named it because it's universal, synchronous, and then they say asynchronous next, and then receiver transmitter. So all you do is you add a clock. CLK. So that clock gives you some synchronizing capabilities, so you don't have to match baud rates anymore. But yeah, not super common. But you'll often see it in microcontrollers. Like you can use some of the pins as USART/UART. But I usually use UART.
We don't have
Okay.
that on the TMSI 70, right?
I don't think so. It's in the 32, I think. And some of the other maybe older microcontrollers have this, but I'm sure there's some specific application for this. I just haven't come across it yet. But yeah, I guess it exists for a reason. I wish I knew what that was, but here you go. Okay, that's one.
I have a question. Sorry.
Jono, let's go.
So you like say you have an Arduino and there's like GPIO pins on it. Can you configure those pins to act like a UART system, or can you only use the UART pins on the Arduino to do UART stuff?
That's a fantastic question. So usually, the Arduino has a little. Okay. Let's say this green thing is your Arduino, right? And you have a bunch of pins and stuff. You have a USB connector and a power jack and whatever. And I drew this blue box too big, but then you have a microcontroller, looks kind of like this. And then the traces go out to a bunch of pins. Inside the microcontroller, there's going to be a little hardware peripheral, a little piece of silicon that Atmel has designed to specifically do the UART handling for you. UART. UART. So it's going to be really easy and a lot faster to use that module with those specific pins attached that are the UART pins, because there's going to be a lot of underlying silicon that's handled to do it. So things like internal buffers and shift registers that can do the communication protocol really quickly. It's like optimized to send start bits and stop bits and exactly the UART data format. And usually that's the recommended thing to do. But if you want, you can actually just use any generic GPIO pin, right? Because all it is lows and highs, right? And we can do that with GPIO. But then you have to basically create the whole protocol yourself. You have to actually make sure that you're doing all of this stuff with start bits and stop bits and parity bits and data bits, and actually set it up in the right way. And usually what people call that is bit banging. So you can bit bang You can bit bang the UART protocol just with GPIO pins. It's not going to be as fundamentally fast because that hardware isn't in place to do exactly those transmissions. And you're going to have to write a lot more code to actually write that protocol yourself. So usually with that hardware block in place, you're going to get a driver function for that. And basically all you would have to do as the user is say UART send in your function, right? UART send and then my data, right? And then you can call it a day, right? You'll have to initialize it and do a few other things, but that's essentially the gist of it. If you're bit banging it and you're writing it all from scratch, you're going to have to specify like start bit, data, stop bit, exactly how fast you're going to toggle these pins. So the baud rate, you have to be very precise on that. And you have to do all that from scratch. So it's definitely possible, but a lot harder, more work, and a lot more code to write than just using the built-in pins. Does that make sense?
Yep, that's cool.
Yeah. So you can bit bang almost anything as long as you have the right voltage levels available to you. But it's much easier to just use what's built in. But a lot of people do it for fun, right? You'll really, really, really learn the protocol like insanely well if you bit bang it because you're basically recreating it from scratch. So you're going to be an expert. But most of your time is going to be spent doing that instead of actually, like, for example, talking like amongst the BMS. You're going to be spend all your time doing this. But if you have time and you're curious, then that's definitely a cool project to take on. Cool. How long have we been going so far? 1 hour. Amazing.
There is major disadvantage to bit banging, just that you're not using like special hardware for the specific like UART or whatever, and so you don't have access to the interrupts and like registers and all that stuff, and so it would take a lot more time from like the operation of the microcontroller to do that, I think.
Yeah, exactly. Yeah, I'd say so. Yeah, I think so.
Because UART is like a hardware thing, right?
Yeah, almost all of these have like SPI, S2C, CAN. They'll have a hardware controller inside with registers, interrupts, buffers, shift registers, all set up ready to go to do it really quickly. If you do it yourself, it's going to be a lot slower.
Okay. Yeah, I thought I was under the impression all the controller like brain or not like some small stuff like that.
Yeah, so in the microcontroller you have the little processor brain part, but then for every peripheral, like even for GPIO, there's a lot of little hardware inside the silicon that's designed to do one thing really well. So either be a GPIO really well, be an ADC pin really well, do UART really well, SPI, S2C. And so that's like the optimized way to go, and it's going to be the fastest way and the least effort. But it is possible to do it yourself. It's going to be a lot slower and a lot more work.
Gotcha.
Yeah, but if you just Google like Arduino, bit bang this, there's like a bunch of people on DIY forums who do it for fun. Cool. So there's a billion more. Some of the more common ones are these. We use all of these in our car as well. Next week we'll go over more later in detail. I don't want to take too much time today, but just high level, I2C is This is called I squared C. So it kind of looks like I and then squared C. It's called something very stupid, called integrated circuit, I think. I didn't get that wrong. Integrated. I don't know who came up with that. If someone knows why that makes sense, please tell me, because I don't know. But then they just took the I's and made it squared. SPI serial peripheral interface. And then CAN is controller area network. Different applications for different different communication protocols for different applications. CAN is really good in noisy environments. SPI is really fast but more wires. I2C is slower but less wires, right? And then CAN is just pretty robust, relatively slow. And we'll talk about these more as the weeks go on. Questions? Need 3.
Do you know of any like other thing that helps the reliability of CAN other than the fact that it's twisted pairs? Because you can do twisted pairs with UART to like do the same noise effect, noise canceling.
Like just twist the TX and RX wires?
Yeah. Wouldn't that achieve the same thing?
Yeah, that's a good question. So people always talk about CAN like this, right? So you have one wire that's called high, and you have another wire that's called low, right? And then we draw it like this because we literally take the 2 wires and we twist them as tight as possible and try to minimize this area. Way back to physics, you create an EMF with like flux lines cutting through areas, right? And if that flux is changing, then you're going to create a little bit of EMF, and that creates a little bit of noise on the line, right? So if you close this area as much as possible and make it very tight, you're theoretically minimizing the amount of noise that you can get, right? So that's great. The reason CAN is more robust than something like UART is because the 2 signal lines are a differential pair. So what that means is that they basically act as one line. Even though they're 2, you don't get that transmit and receive operation that you do with UART, right? It's not full duplex. You can only send and receive one thing at a time. So these are 2 separate lines in UART. In CAN, they're related to each other very much so. And how they work and the way a differential pair works is that when one line is high, the other line is low, right? So they're exact opposites. Some people even call them like CAN positive and CAN negative. So they are exactly opposite to each other. And what that means is that when the slave receives them, or whoever you're talking to receives them, so if this is CAN high, this is CAN low, what they basically do is they subtract the 2. Right, so say CAN high minus CAN low equals what, right? And if you're subtracting the 2, like let's say this is, just for argument's sake, this is not actually what it is, but like if this were 100, like size 100, that's, I swear it's 100, oh good. So it's like this, 100, then this would be negative 100 maybe, exact opposite, right? So when you subtract 100 minus negative 100, you get 200, right? Then you can just divide by 2 and get what the height actually was, right? 100. Now imagine you get a little bit of noise. So you get a little bit of noise here. right? So maybe what I'm actually seeing is not 100, but 106 because of the noise, right? Because we've twisted the pairs so closely, the noise that shows up on one line is going to be the exact same noise that shows up on the other line. So if I saw that amount of noise on my high, I'm going to see that exact same amount of noise on my low, right? So if I had 6 of noise, let me just double check something quickly. 6. So if I had 106, so like this is total make-believe, right? But I added +6 of noise here, right? It's not actually how it works, but just for argument's sake, I would have the exact same +6 of noise here, so that'd be -94, right? For example. Now when I subtract them, oops, 106 minus -94, what do I get? Can someone give me that? They're same 200, right? So no matter what noise I get on the high line, because I've twisted them so closely, I'm going to get the exact same noise on the low line. And because they're a differential pair, exactly opposites in each other, when I do that comparison and subtract them, I basically get to subtract away all that noise that's identical on both lines. So that's what makes it extremely resistant to noise and makes it really good in a noisy environment like a car. Does that make sense, Mahmoud?
Yeah. It's funny though, the UART on the BMS is actually twisted pair. I think I just thought about that during the moment. Because it has 4 wires, 2 wires for RX and 2 wires for TX.
Yeah, so are the 2 RX ones identical? Like the exact same signals on both?
Yeah, like it's differential, like plus and minus.
Nice, exactly. So that's a really robust UART, right? You have a TX and RX still, but now it's split into TX, for example, high, and TX low, or TX plus and TX minus, right? So then with each of these, then we do the exact same differential communication to make it super robust. But yeah, that's why. Differential, you just collect the same noise on both, and then you subtract them, and then the noise goes away. So that we actually do that with the daisy chaining between BMS slaves as well. And sometimes people call these plus and minus instead of like high and low. High and low is usually specific to CAN, plus minus is not. So wherever you can do that differential pair and then twist them, you'll get a really robust signal, which is important for BMS. 2 more questions.
Okay, since you're going off of CAN, question about CAN again. Is this noise thing the reason why the SAE really likes CAN? Like they have their own like protocol, J19 something.
Yeah, J1939, I think. I'm sure you use a lot of it at Ballard. Surush loves CAN, but so does so does the world, right? It's in almost every car. SAE standards for automotive. Really love it.
Everyone says this. The phrase is "no can do." I'm like no can do.
That's so funny. Yeah. Yeah, if you're in the automotive space, you're going to use a crap ton of it. It's just so reliable compared to everything else because of this. And not only this, but then the actual like data format is a lot more complicated than something like UART. So it's pretty robust. A lot of error checking. But yeah, that's it. Last question.
Or the stop and start bit, is that something you predefine to say it's going to be low? Or is that just the standard?
I think that's the standard. Correct me if I'm wrong, Mahmood. Is there a like active high start and stop bit?
No, I think that's just
Usually-
part of UART communication.
Yeah, I think usually the line floats high and then they pull it low to start.
Yeah.
But like you can make your own UART, call it JART, and then Jared decides whatever he wants. Make it active high start bit, and the line floats low, or idles low.
I squared C is the opposite of UART, I guess, in that sense.
Yeah. I2T is like axe and nax and a bunch of shit in there, which we'll talk about next week. Right. We're done. Thanks, everyone. See ya. Oh, question. Sorry. Can you do all that with inline assembly? Which part? Sorry, Courtney?
I don't quite remember.
Yeah, sorry.
What it was about.
You could probably do all of it with inline
Oh.
assembly if you want.
Bit banging?
It was with the registers, like accessing the registers and interrupts.
Yeah. Even in assembly, you wouldn't have access to them if they're not configured to those pins.
Oh, I see.
Yeah, it's like the underlying circuitry and the silicon underneath connects them to the specific UART pins. And whether you use assembly or not, you still wouldn't have access to them if you bit bang on your own GPIO. The assembly would make the C functions and function calls you do faster, but it wouldn't gain you access to those registers. For us, which do we use more of in our code? SPI for sure. That's basically only because of basically of what our sensors need, like based on the chips we picked and the underlying circuitry in them, we have to talk with them over SPI. So only one of our chips is I2C, and SPI is so much easier to use as well. So I love it. But yeah, SPI for sure.